Good morning, dear participants, ladies and gentlemen. Welcome to the fourth capacity building webinar of the Low2High district heating project on the topic integration of low-grade energy renewable energy sources in high-temperature district heating. Speaker is Professor Vincenzo Bianco from the University of Naples, Partenope. Welcome, Vincenzo.
Thank you, Martina. Thank you for the introduction. Good morning to everybody. So I tried to activate the subtitles, but I can choose just one language. And also I choose the English, and now it's not working, so I don't know what to do. I can try to activate in Teams the subtitles, but I guess that if all the guests activate in Teams the subtitle, they can choose their preference language. So technically, I don't know. But however, Martina, can you confirm that the screen is correctly shown?
Yes, I see your screen.
Okay, so I would go ahead with the presentation. So we are going to discuss the integration of low-grade energy, renewable energy sources in high-temperature district heating. First of all, let me inform you that this webinar is being recorded, and so if you don't want to show yourself, please close your camera, or if you have a specific concern about the registration, the recording, please just inform us, or in an extreme case, just leave the session. So having said this, to inform you, let's start with the presentation. We will try to keep it as short as possible, but enough to provide you the relevant information. So we will discuss quite briefly these 8 points. We will have an introduction, some integration schemes, and a set of examples of solutions for RES integration at different levels. So, first of all, here you have an overall picture of how district heating generation progressed in the European Union, and how the share of fossil fuel generation has been decreasing and replaced by renewable generation. Other sources like nuclear are negligible. You can see it here, but in some countries, including Slovakia, there is some nuclear generation. So most of these renewables that are spreading in district heating generation is represented by biomass. So basically, you substitute the burning of coal or natural gas with solid biomass in particular, and a small fraction is represented by biogas or biomethane. So this is what's going on at the moment. This is the trend. Here you can see how other renewables are diffused, and you can see, I mean, the sum on over each column will be 1, and you can see the European champion in total RES generation. So in the total share of district heating generation in terms of RES is Sweden. But for geothermal, we have France, even though geothermal is a small fraction of the renewable district heating generation. For solar thermal, we have that Denmark is the European champions. Heat pumps are very popular in Sweden, and also solid biomass. You can see that Sweden, Finland, and Denmark are European champion in terms of total share of generation. But also we have Lithuania. It's 4.3%, but because Lithuania is a small country, so the overall generation is low. But if we analyze the share of biomass, in the Lithuanian district heating generation is pretty much high. In Italy, we have a substantial generation of biogas, like in Germany, and then we have also the RES part of waste incineration, that again in Denmark, Germany, or Sweden is very popular. So this is the picture on how at the moment renewables are used within district heating generation. So in this picture, you can see an approximate classification of this district heating sector. This is a classification you can find in many reports, in many papers, and so on, even though we must say that a formal classification of district heating network does not exist. But however, this one is commonly accepted. We are mainly consider district heating network of the third generation, those developed in the 60s, 70s, where we have temperature in the network at around 100 Celsius degree. It can be a little bit above, a little bit before, a little bit above, a little bit lower than 100 Celsius degree. And these are district heating network we have considered. As you could see in previous webinars, we presented some concrete cases of applications. So the idea is how to integrate low-grade energy renewables into this network. Let's say that with low-grade renewables, we consider renewables energy sources with low energy density. But to exemplify this definition that could result a bit complex and tricky to understand, we can say that we are referring to low temperature energy sources, basically. So these sources, before used in this network, needs a kind of upgrade, because we cannot inject directly in many cases. In other cases, as we will see in the following, we can also imagine to have a direct injection of thermal energy. So basically, we are on this side, you know, we are working on this kind of district heating network, or between these two, depending on the specific case. So how this integration works? So we have a set of sources that we can consider to be integrated in this network. And maybe somebody has the microphone switched off. I ask everybody to switch off the microphone, or we have some background noise. So these are different sources of low-grade energy that we can use to supply district heating network. But here you can see two technologies that are relevant that we can call enabling technologies, because without heat pumps in particular to increase the temperature level and so to apply the so-called temperature escalation, we will be unable to, for example, recover heat from shallow geothermal or municipality heat waste, industrial heat waste, and so on, because usually the temperature level of these sources is not compliant with the temperature level required by the network. And so we need to increase the temperature before injecting in the network, and then we can distribute this heat. This is not the technical framework on how to do this, but it's the conceptual framework. Then we may consider also the integration of heat storage to support, this mechanism, because in some cases it could be useful to decouple the source of heat from the network, and the decoupling can be done through heat storage, as we will see in a moment. So how is the system? How is the current situation and the future situation? The current situation is where we have fossil fuels everywhere. So we have a CHP plant, or we have boilers where we burn fossil fuels we generate heat in form of vapor, of steam, and this steam is then distributed to the network. So we may have steam in some parts of the network, we may have hot water, and so on, that is distributed. Now we are trying to focus on the integration. You know, we are trying to push this intermediate step where we mix this fossil fuel generation with some renewables, and so try to achieve an integration, and then the network, the rest of the network works in the same way. The ambition, the final ambition, is to have a fully renewable-based district heating network. But as you know, we need more steps and more years to arrive to such kind of solutions and more technological innovations to have it. So let's see now which are the integration schemes, because we can have three main schemes of integration that you can see: A, B, C. So if this is the primary side, this is the user substation, and this is the secondary side, the integration can be done in different ways. We can make it on the secondary side only, and so the local renewable, the local thermal renewable energy sources are exploited only by the user. And this is the scheme A. Then we have the scheme B, where we have the prosumer, because we have the decentralized thermal renewable energy sources that can be partly used by the user and partly transferred to the network. You can see that the connection is usually on the return line. Or we may have a decentralized source connected directly to the primary side, and so the thermal renewables is distributed to the network. So these are three kinds of integration we can imagine. Obviously, the easiest one is the option A, because you generate thermal energy locally and you use it locally. So the primary side is not affected basically by the decentralized generation of thermal energy. Then, how to integrate on the supply, return side, and so on. The easiest thing is to integrate the renewable, the thermal renewable on the return, on the two return lines. The main options is to integrate on the return and supply line. Okay, so we have the integration on the supply side, and then on the return side when the waste heat is returned. Which one to use? You know, we cannot say in advance. It depends on the network. These are different options. Then there are also other options like double integration on the supply side, or supply return integration that can be usually considered for safety measures. For example, to lower, to protect from overheat. For example, if solar thermal installations are considered, especially solar concentration power plants that we are going to see in a moment. Then, let's see some examples for RES integration. So, we have, we considered three kinds of interventions. One where we don't work in the network, but we work on the main heat generation in case it is a CHP. So we provide the renewables integration not on the network, but directly in the CHP plant. And this is one set of solutions. Then another set of solutions is the integration of renewables with boilers that you can have in the network. And a third option, the most radical one, is the substitution of the boiler with a renewable energy system. So this is the full renewable options that can be applied, but not in all the cases. So now let's see some solutions focused on the integration directly in the CHP. So basically, the idea here is to use renewables to preheat the water before entering the steam generator. With the through renewables, we can increase the temperature before sending to the steam generator and save some fuels in the steam generators. So this means that part of the steam or the hot water distributed in the network is already generated with renewable sources. This means that we need to have the possibility to connect the CHP to renewable sources that are located around the CHP installations. And whatever is the kind of renewable sources, we can do this integration. For example, solar thermal can be used here, and we have an example here, a reference project in Högslätten in Sweden, where in 2023 a solar thermal park was committed, and the heat from the solar thermal field is generated at a temperature between 73 and 120 Celsius. So you can directly generate steam if you are in the high part of the temperature level. This is the solar concentrated technology we are discussing about, so parabolic concentrators, and take into account that we are not talking about futuristic things or research things, because there are companies on the market producing these installations that, for example, are getting popularity in the food processing industry, because with these levels of temperature around 150 Celsius or a little bit lower, you can run most of the processes related to the food industry. And so you can use it also in district heating, because we need the same temperature levels. Because if you consider the energy waste in pipe and so on, finally you arrive that the steam in the pipe will have temperatures around 100 Celsius degree. An objection could be that in the countries we are talking about, Lithuania, Slovakia, and Poland, there is no sun. But this example is from Sweden. But you are right that there is no sun, especially in winter. But what could be assumed, what could be considered, is that during summer period you need hot water. You don't need heating, but you need hot water that comes from district heating. So what it can happen if you imagine the system into an integrated logic, and for example in winter you support your system with biomass, with solid biomass, for example, to replace coal, you can suppose that in summer you can leverage on the relevant support from solar generation, because you have long days in your country. If imagine to Lithuania, the northern part of Poland, for sure you have a long day and sufficient radiation to generate this hot water. So you can store, you can save biomass in summer to be used in the winter. So if we want to achieve the decarbonization, you need to think into an integrated logic. You cannot have everything in the same moment, but we need to consider an integrated logic. And it's interesting to note that this kind of observation was also given by the president of the Lithuanian District Heating Association. On the press, I read such kind of this interview, that it is very illuminating. In fact, you have some prototypes, I mean, a pilot plant similar to this also in Latvia, for example, which is very close to Lithuania and the northern part of Poland. So we are talking about real objects that in some cases are already in place. Then here we could use a flat bed solar panel, so not solar concentrating solar panel. Flat bed are a simpler object, and you reach lower temperature like 50, 60 or 70 Celsius degrees. Then you have two options: or you use the water at this temperature, and so you have a less renewable integration, or you can use a vapor compression heat pump to increase this temperature, also at the level where the boiler is not anymore necessary. But we need also to consider the flow rate of water we manage to heat. Again, the vapor compression heat pump is a relevant technology in this context, because without its utilization, most of the solutions we will see that I am proposing could not be considered. And more interestingly, we can use steam vapor compression heat pumps, where vapor steam is considered as the refrigerant. We can do this because the lower temperature of the cycles are not below zero, but are in the order of 30, 40, 50, 60 Celsius degrees. So we have relatively high temperature. And this is a very relevant advantage, because the environmental impact of these systems is very low. The main source of energy we need to provide here is the electricity to run the heat pump. So then it's a problem of analyzing how the power system in this country is supplied. For example, if all the energy comes from coal, or most of the energy comes from renewables. This is a very important aspect in the overall analysis of the energy system. And secondly, another very relevant aspect is that in this kind of heat pumps, you don't have any kind of refrigerants. So the heat pump individually has a very low environmental impact, because you don't have any kind of a toxic and environmental harmful refrigerant. So this is a very relevant advantage here. Then let's see solutions involving boilers, where you can see a massive utilization of heat pumps. So, for example, here you can install on the return line of your district heating. You can heat, the water from the return line with solar energy by using solar panels. That could be solar concentration or flat plate panels. And depending on the temperature level you reach, you can completely bypass the boiler, or you can enhance the temperature of the steam before entering the boiler. So the energy you need to supply to the boiler is much less than in a configuration without having the solar integration. So here we propose the solar integration, but we can see that this integration can come by different sources. For example, here is another approach where you use a high temperature parabolic solar integration at very high temperature, and so you can supply directly to the network. And so you bypass the boiler somehow, but when the temperature is, when the solar radiation is not enough to achieve such a kind of high temperature level, again, you can support the boiler by providing some energy before sending the steam to the boiler, and so the energy you can supply in the boiler is lower. This is a flexible approach because in some parts of the year, suppose you can supply the network directly with the solar thermal field and you don't need the boiler at all. In some other part of the year, you need the boiler integration. In some other parts of the year, the coldest part of the year, probably the solar collectors cannot provide any benefit. But we come back to the integrated logic I was mentioning before, because you cannot have an overall solution, one turnkey solutions that can solve all the problems. So you need to integrate different technologies in this new vision of district heating network management. Then, this is another important source of energy, that is to recover waste energy, especially where you have large power plants. Here you have two options. One option is reported here in the chart, where if you have a large amount of heat available as industrial waste heat, we can imagine to use absorption heat pumps. Absorption heat pumps have the advantage to use very little energy to work, but their COP is very low. It like 0.25. It means that to have 1 megawatt of heat at the desired temperature level, you need 4-5 megawatt of waste heat. So this solution is feasible if you have a very large amount of waste heat that you can recover. This is also a not expensive solutions, and again, you can integrate with an existing boiler. What is important is that the industrial plant has a more or less continuous cycle, because if the waste heat of the industrial plant is missing, clearly all the system is stopped. So you need a continuous generation of this waste heat. If you want, you can improve this solution by decoupling the heat pump from the waste heat generation through a heat storage system. Because if with the waste heat you feed the heat storage system and you connect the heat pump to the heat storage system and to the network, you decouple the heat pump from the industrial plant. And so you have a buffer where in case that for some hours the plant is not delivering the heat is in the heat storage, and you can keep on running the district heating solutions. Clearly, you cannot have very long term heat storage systems because they will be very, very big. So, another solution instead is to couple a waste heat source with a steam heat pump, so a vapor compression heat pump based on steam, where the COP is much higher than the solution seen before, because the COP here is around 3-4, and you can increase the temperature at 100 above 100 Celsius degree easily. But you need electricity, much more electricity as main input. So depending on how electricity is generated in your country, this could be a sustainable solution or not. In countries with a high level penetration of renewables, such as Sweden or Denmark, as we saw in the previous example, these solutions is quite effective and also quite popular. In fact, if you remember from the previous chart, we have that in Sweden, a lot of heat is generated through heat pumps that are considered renewables if they are fueled with renewable energy. Then here we have instead a set of solutions where you basically substitute the boilers and use directly the renewables or the waste heat. So here what we can do, this is a generic schematic where you can combine a water steam heat pump with a generic low temperature source. So this low temperature source can come from solar energy, from waste heat, from shallow geothermal. Another solution very popular in Sweden is shallow geothermal. So geothermal at low temperature, we see an example in a moment. So you can use the heat pump to increase this temperature level and directly inject in the network. Usually in such kind of system, you always want to have a thermal energy storage to absorb the fluctuations that you may have into the renewables or waste heat intermittent source. Because with the thermal energy storage, you can absorb some fluctuations and go ahead. And go ahead with the system. You will get this presentation, and in this presentation you have also the average cost of energy generated by the different solutions. So you need to compare this average cost directly with the cost of fuel. That could be natural gas, coal, or whatever. But obviously, this depends. The convenience of this system, the economic convenience, depends on the gas price, on the gas price, oil price, the commodity price at the moment of the comparison and the overview you have for them in the long term. However, when you make the financial comparison, depending on your point of view, you can include more sophisticated approaches, because you need to consider that if you are like a public body, you need to include also the externality cost, negative externality deriving from fossil fuel solutions, including, for example, the energy dependence. That was one of the main variables that pushed Lithuania to dismiss natural gas in their district heating network and shift almost all the system on biomass. So the considerations that you can apply are of different nature. Then here, we proposed this solution that conceptually is not different from the previous one, except for the utilization of a specific source of waste heat. That is the aerobic or anaerobic digester. Probably there is a typo because here is anaerobic digestion. Why we proposed these digesters that are usually considered in the treatment of the organic fraction of waste heat? Because these technologies in the waste treatment strategies released by the European Union is considered as the main technology. Since these devices generates temperatures inside their process of 70-75 Celsius degree, we can efficiently exploit this source of energy that is continuous, because waste generation is continuous in cities, and in perspectives you will have these objects in many cities all around Europe, because it will become the main source for treating the waste, the organic fraction of your waste. So this kind of source has all the features that makes it attractive for being integrated in a district heating network, because it is continuous, so we have a steady supply of it. It can be coupled with a water steam heat pump efficiently, and so we can completely bypass the utilization of fossil fuels. In addition, this represents also an industrial symbiosis example, because the waste from one industry, the waste treatment industry, becomes an input for another industry, which is the other industry, the district heating generator. So this is a fully virtual solution, a fully virtual hypothesis to explore. So, for example, if there are some responsibles of municipal utilities and so on, you can relate to your colleagues in charge of waste treatment and see if there is this kind of opportunities. There are also examples of pilot plants around Europe of such kind of solution. Then this is the solution including the shell of geothermal, where if we assume that the seasonal temperature of the soil is around 10 Celsius degree, we have we can extract this heat through a geothermal heat pump for a first temperature escalation up to 50-60 Celsius, and then with another water steam heat pump, we can move from 50-60 to around 100 and inject directly in our district heating network. This solution, as you can imagine, is a bit more expensive. Why it is more expensive? Also simply because you need to have two heat pumps instead of one, because with just one heat pump you are unable to escalate the temperature from +10, +15 up to around 100. However, let's say that this solution is also very popular in Sweden, where you have many of these kind of geothermal geothermal heating system. Then this is another interesting solutions for cities, and there are also here very different pilot plants, that it is the utilization of sewage water. Why this is a good option too? Because in cities, sewage water is a stable source of energy, and it has a stable production, so you can easily foresee the amount of sewage water that is flowing in the sewage pipelines. In average, this water has a temperature around 15-20 Celsius degree. So with a vapor compression heat pumps, with a single heat pump or with a double heat pumps, it can be easily upgraded up to 120 Celsius. So what's going on here? So the problem is always the same, that vapor compression heat pumps are driven by electricity. So the solution is fully renewables, provided that you have a good power generation mix. Good means with a substantial share of renewables or nuclear. Finally, we are almost at the end. I want to present you a recent example of integration of waste heat from data centers. And this is an example of from Finland, from Helsinki. This is a real case where you have that heat from data centers, from underground data centers, are considered as a source supplying the district heating network of Helsinki, in particular this district, Expo, Kirkkunniemi, and Kauniainen are involved in this project. So how it works? You have the district heating, you have the data center providing heat at 30-40 Celsius degree. Then this heat is upgraded with a heat pump having a COP of 4, so 25% electricity. It means COP of 4. And then if you need an increase in the peak temperature, you can use electric boilers. Then it's sent to the network, and you have this heat is exploited. Then it returns to 20 Celsius degree, where this water is used to cool the data center, and so on. And you can see a virtuous integration of waste heat into the district heating network. What is the advantage? The advantage is that the data center provides a stable source of heat because they run 24 hours, 365 days per year. So you have the stability of the source. And as far as I understood, so here you have some references also. Municipality of Helsinki is making agreement with these, big tech company that needs these powerful data centers like Microsoft, Google's, and so on. They are making agreement to host these centers in their cities with an underground configuration, because they will recover this heat, and this is a smart way to decarbonize the network. So let's jump to the conclusions. We had an overview of different approaches to integrate existing district heating network operated at a temperature around 100 Celsius degree with renewables or with waste heat. The easiest interventions are on the supply line, as you could see, and so the interventions on the supply line usually are focused on reduce the amount of fossil fuels provided in boilers or provided in the CHP. But in some cases, you can act directly on the supply lines because you manage to reach the desired temperature levels. So, for example, by using vapor compression heat pumps, you can easily reach temperatures in the order of more than 100 Celsius degree, starting from a waste energy source of 60, 50, 40 Celsius degrees, or from a renewable source, clearly. So in this case, if the source of waste heat or of renewable heat is stable, you can connect directly to the supply side. However, usually it's preferable to decouple the source of low temperature energy from the network through an energy storage system, because you can absorb the fluctuations, possible fluctuations that you may have in the temperature profile, unless you are sure, 100% sure, that the supply, the energy supply is very stable, as is the case of data centers. Then let's also say that in the study, the analysis of these preliminary solutions, we focused on low invasive interventions that will not change the overall logic of the district heating network, because to change the overall logic of the district heating network, would mean to invest a huge amount of money from one side, and from one side to have a very, very, very strong commitment that in many cases is not available. Commitment in the sense of to start time-consuming and invasive works in the networks, in the buildings, and so on. And to be realistic, instead, we must consider also acceptable technologies. I mean, acceptable for the general public. Then you understood that the role of heat pumps, so an enabling technology, a temperature upgrading technology, it is mandatory. Then it's important to evaluate how power generation is developed in your country. Because if power generation is mainly based on hard fossil fuels, coal, lignite, and so on, then in terms of overall emissions, these solutions could be questionable. Thank you very much for your attention. Sorry, before leaving you for the questions, let me also add that these are, conceptual solutions that we proposed, we tried to analyze. In some cases, you see some case studies that we tried to apply in Lithuania, Poland, and Slovak. All the cases you have seen applied stemmed from this proposal that was from the solutions you have just seen that were preliminarily developed, and then they represented food for thought from your colleagues in Poland, Slovak, and Lithuania, which operationalized, in concrete terms, some of these solutions and make proposals with a real business case that we are trying to complete. Thank you very much for your attention. If you have questions, I will be happy to answer.
I have a question.
Please.
You describe on the scheme utilization of heating pump with turbine. So is it realistic, this concept, that you would like to use energy to
No, it's just a schematization. I mean, we are talking about available industrial available water steam heat pumps. That is a technology used popular in industry, in production processes, where refrigerators is not represented by the refrigerator fluids like RR134 or others, but you have steam, water steam. Why you can have water steam? Because the lower temperature of the cycle is not -10, -15, or minus something, but it is +30, +40, +50. And so you have you generate vapor at this temperature by making under pressure, and then with the screw compressor you increase the temperature of the vapor, and so you can reach this 100, 120, and so on. Where is the drawback in this solution? The drawback is into the electricity consumption, because even though the average COP you can reach in these solutions is 3, 4, and so on, if the electricity you are using is mostly based on coal or something, finally you are using fossil fuels with a low efficiency. If this is the case, then it's better to burn the coal and generate heat. So these systems work if well integrated in a renewable-based power system. That's why they are very popular in Sweden, in Denmark, where you have a high level penetration of renewables in the power system, for example, through to wind power, offshore wind power, and so on. On the other side, they can work also in places where you have a high level of nuclear generation, because nuclear power has no carbon emissions or atmospheric pollution connected. I mean, you have other kind of waste to treat, but that is a different story.
Thank you for explanation. So just to make it clear, mainly the production of the steam from heat pump here is mainly for the reason that there is possibly some customer from the industrial side who need steam. Is it correct or?
No, but the steam is used within the heat pump as the refrigeration fluid. Okay, so it operates the steam as the refrigeration fluid. So that's the point. Yes, as you said, you can find industrial solutions where these, I mean, the industry that are using this kind of heat pumps are using them with steam because they need the steam. But let's say that in most of the industrial processes, in many industrial processes, for sure in food processing, that is a relevant part of the process industry, you use steam. But also in pharma industry, you use steam. So water steam is massively used in all the industrial sectors. And what I want to highlight is that these water steam heat pumps, it's not a new object. It's not something fancy, something coming from up-to-date research, something that has been working for 20, 30 years in the process industry. So we are using something very well known. And I think that this is important for your analysis, because we are talking about a reliable object already used in industrial context, where already you have a supply chain, very well established supply chain, you have manufacturers of these objects and so on. I invite you to just Google it and look around. You will find many market solutions for this kind of devices.
Thank you very much for answer.
Yeah, you are welcome. Okay, then if we don't have other questions, so I think we can stop here. We are perfectly on time, I would say. So thank you very much for joining our webinar. I hope you find it interesting. Follow our project, because you can get the recording of the webinars, maybe with the subtitles in your language from one side, but from the other side, you can download a technical report where these the solutions I presented are described, analyzed, and so reference, and so it can become even more useful for you, because you have a written reference that you can analyze yourself and, if necessary, to use. However, feel free to reach us whenever you want for information, question, discussion. We are open and available for this. Thank you very much.
Thank you, Vincenzo, for your excellent presentation. As dear participants, we appreciate your participation and thank you for your attention. You are also invited to attend a webinar that will take place next Wednesday, 11th March at 9:30. The topic of the webinar will be Core Financial Concepts and Analytical Approaches for District Heating Site Renovations. and it will be presented by Álvaro Salamanca from the GNE Finance. So thank you very much and have a nice day.